Module 4, Lecture B, Zip, Map, Filter. By the end of this lecture, you will be able to use Zip to combine multiple iterables into tuples, handling length mismatches appropriately. Apply Map and Filter to transform and select elements from iterables using functions or lambdas. And convert lazy iterators from Zip, Map, and Filter into concrete collections using other built-ins when needed. Pairing iterables with Zip. Basic two-sequence Zip. The Zip function pairs elements from two sequences so you can process them together in a coordinated way. For example, if you have a list of student names and a list of their grades, it matches each name with the correct grade. It does this by taking the first element from each sequence as a pair, then the second from each, and so on. You can think of it as turning two separate streams of items into one stream of bundled pairs, which is a useful idea for more complex data processing tasks. When related data is stored separately, such as product IDs and order quantities, zipping them together lets you handle each product alongside its quantity in a single pass. This makes operations like calculating totals or generating invoices more direct and organized. The same idea applies when pairing dates with temperature readings, which supports natural, time-based analysis. In both situations, zipping combines two aligned data streams into one stream of paired records that mirrors how the data is connected in the real world. When you zip two sequences, you get a lazy iterator that creates each pair only when it is needed, instead of building all pairs in advance. This saves memory and can improve performance, especially with large datasets, such as long customer lists and account balances. If you later need to store or further process the pairs, you can convert this iterator into a list or another collection. Understanding this trade-off between on-demand generation and storing results helps you use zipping efficiently in your programs. Python code. Basic two-sequence zip. This example shows how to use basic zip pairing with two related sequences. We pair student names with their corresponding test scores, so each name is matched to the correct result. Because the zip operation creates a lazy iterator, we then convert it into a concrete list, so the paired data can be easily viewed or displayed. We begin by creating a list of student names: Alice, Bob, Carlos, and Dana. This list will later be matched with a separate list of test scores. By pairing each name with a score, we can clearly associate every student with their performance. This structure makes it easier to organize and work with the data. We create a list of scores that holds numerical test results, where each score matches a student from an already defined list of names. This means every student has a corresponding test score stored in the same position in the scores list. With this setup, we can easily connect each student to their score and use that pairing for tasks like organizing or displaying the results together. The zip function lets us combine two separate lists, such as a list of student names and a list of their test scores. It pairs each name with its matching score, creating a sequence of name-score pairs. This effectively lines up the two lists so that related pieces of data are grouped together. As a result, it becomes easier to work with and manage information that belongs together, but was originally stored in separate lists. We convert the zip iterator, which is a lazy object, into a list of tuples so that the paired results become concrete and directly usable. Turning it into a list stores all the paired data in memory, making it easy to loop over, inspect, or display. This step prepares the data for any further processing or output we might need. The code first prints a header that introduces the results that follow. This header is a short description explaining that the output will show student names paired with their test scores. By doing this, it clearly sets the context, so anyone reading the results understands what the data represents. In other words, it labels the output to make the information easier to interpret. We loop through a list of paired results, and in each pass we split the pair into a student name and a score. For every pair, we then create and print a clear sentence that states the student's name and their test score. This process shows each student's performance in an easy-to-read and understand format, highlighting the connection between names and scores. This script shows how to use the zip function in Python to combine two related sequences. It takes a list of student names and a matching list of test scores, then pairs each name with its corresponding score. The zip function produces an iterator of pairs, which is converted into a list, so the results are easy to display. When run, the program prints a short header, followed by sentences that state each student's name and score, illustrating an efficient way to merge and iterate over two sequences together. Zipping multiple iterables. Once you know how to pair two sequences, you can extend the idea to 3 or more by creating tuples that take one element from each sequence at the same position. You can think of this like walking through several parallel columns of data, such as student names, majors, and grade point averages, all at once. Each step through the data gives you one combined record that includes all the related pieces. This lets you handle multiple sequences as a single stream of structured records and avoids the need to manage positions with manual indexing. Combining multiple iterables is useful when related data is stored in separate collections, such as product information in business or measurement data in science. By zipping these collections together, you can work with each complete record at once, which simplifies tasks like generating reports or checking for anomalies. The important idea is that the resulting tuples preserve positional alignment, so first elements are grouped together, then second elements, and so on. This automatic alignment helps prevent mistakes that can occur when you try to coordinate separate lists manually. When you zip together more than two iterables, it's important to give each position in the resulting tuple a clear and consistent meaning, such as city, country, and population, or date, opening price, and closing price. As you write your loops, choose variable names and processing steps that make this structure obvious, so you always know which part of the tuple you are using. This becomes especially important as you combine more attributes, like demographic data or performance metrics. Thinking of the zipped output as a stream of small, fixed records helps you keep the data organized and makes it easier to add more iterables later if needed. Python code, zipping multiple iterables. use the zip operation on 3 related iterables to combine them into structured records, where each position across the iterables is grouped into a single tuple. Each resulting tuple represents one logical data record that brings together corresponding elements from the 3 sources. Choose clear, descriptive variable names so it is easy to understand how the multiple iterables are being combined and how each tuple forms a complete record. We define one list that holds the names of 3 students: Alice, Bod, and Carlos. Then we define a second list that holds their corresponding academic majors: physics, history, and biology. These 2 lists are meant to be used together so that each student can be paired with the correct major in later steps. The code starts by creating a list of grade point averages, storing each value as a floating point number that matches the previously defined students. It then uses a print statement to show a brief header that explains what is coming next. This header tells the user that the program will now display combined records that include each student's name, major, and GPA. The goal is to present these details together in a clear, structured format. We use the zip function to loop over 3 lists at the same time, combining each position into a single tuple that holds a student's name, major, and grade point average. As we iterate, we unpack each tuple into separate variables for the name, the major, and the GPA. For every student, we then print a clear sentence that states who they are, what they study, and their GPA. This creates a simple, organized output for each student record. We begin by defining a list of city names, such as Dallas, Boston, and Denver, each aligned with a corresponding population value. We also create a matching list of country names, all set to the United States, so that every city is paired with its country. This structure lets us combine city, country, and population into a clear, organized dataset ready for further use or output. We begin by creating a list that stores the populations of several cities, with each value measured in millions of residents. After setting up this data, we print a clear header to separate this section from earlier output. This header explains that the following records will describe cities, their countries, and their populations. Using this structure makes the printed results more organized and easier to read. We use the zip function to loop over 3 lists at the same time, pairing elements that share the same position. Each pair forms a group containing a city, its country, and its population. As we iterate, we unpack each group into separate variables and use them to speak a clear sentence that names the city, its country, and its population in millions. This method neatly combines related pieces of data from multiple lists into one coherent, structured output. This script shows how to use the zip function to combine several lists into organized records. It first pairs student names with their majors and grade point averages, then prints each student's information in a clear sentence. It then does the same with city names, country names, and population values, presenting each city with its country and population in millions. Overall, it demonstrates how zip can align related data from multiple lists and let you iterate over them together in a structured way. Handling uneven lengths. When you pair elements from multiple sequences into tuples, the process always stops as soon as the shortest sequence runs out of elements. As a result, the total number of tuples is determined by the length of the shortest sequence. Any extra elements in longer sequences are simply ignored. This behavior is predictable but can be surprising if you expect all elements from the longest sequence to be included. When you pair two sequences of different lengths, the pairing stops at the shortest one. Any extra items in the longer sequence are ignored, which means missing entries, like a student without a submitted assignment, will not appear in the result. The same applies when matching product IDs with sales figures. Only the days that line up with existing product IDs are kept, and additional sales data is discarded. Understanding this behavior is important so you can avoid unintentionally losing data when your sequences are not aligned. When working with sequences of different lengths, you must carefully prepare and validate your data before pairing them. Sometimes it makes sense to truncate sequences, such as when you only care about overlapping parts. But in other cases, you should detect mismatches by checking lengths or logging warnings. You also need to interpret any leftover elements, deciding whether they represent missing data or incomplete records that require attention. By treating uneven sequence lengths as an intentional design decision, you help keep your data workflows accurate and meaningful. Python code: handling uneven lengths. This section explains how the zip operation behaves when it combines sequences of different lengths. When one sequence is longer than the other, zip only pairs elements up to the length of the shorter sequence. Any extra elements in the longer sequence are silently ignored, which is safe and predictable. Understanding this helps beginners know exactly what result to expect when they zip lists of unequal length. We begin with a list of 4 student names: Alice, Bob, Carlos, and Dana, representing the members of a class. This list is created so that each student can later be paired with a score. Setting up the names in this way prepares us to show how the Python zip function works when it combines sequences that may not be the same length. The focus is on using this list of students to demonstrate how zip handles these differences. We create a list of scores with 3 numerical values that represent the scores of 3 students. However, there are actually more students than scores. This mismatch is intentional because it sets up a situation where one student will not get a score when we later pair the student list with the score list. This example is used to show that the zip operation stops pairing as soon as it reaches the end of the shorter sequence. We print the list of student names to clearly display its current contents. This shows the original values stored in the list before we make any changes. Seeing these values provides useful context for understanding later operations. It also makes it easier to compare the list before and after any modifications. We first show the scores list so we can clearly see the original values it contains. This makes it easier to understand the data we are working with. By viewing the list before making any changes, we know exactly what information our later operations will be applied to. We now display a short message to let you know that the next output will show the result of pairing the 2 lists using the zip function. This message signals that you are about to see how the lists are combined into pairs. It also reminds you that this pairing process automatically stops when the shortest list runs out of elements. We use the zip function to combine two lists, such as students and their scores, by pairing elements that share the same position in each list. It moves through both lists together and stops when it reaches the end of the shorter one. Any extra items in the longer list are simply ignored, which prevents errors. The final result is a list of pairs, where each pair contains a student name and the matching score. This example shows how pairing two lists of students and scores works when using a function that combines them into pairs. The function only creates pairs up to the length of the shorter list. As a result, the last student, Dana, is left out because there is no matching score. This illustrates that any extra elements in the longer list are simply ignored. We check the length of the students list to see how many student names it contains in total. This tells us the number of students we are working with. It is especially useful when we compare it with the lengths of other lists, such as scores, to make sure they match. If the lengths are different, it can reveal mistakes or missing data. We check the length of the scores list to see how many score values we have. This is important because we need to match these scores with the students list. Knowing the length helps us predict how the pairing process will work, since the zip operation only creates pairs up to the length of the shorter list. This way, we understand how many student and score pairs will actually be formed. We are finding the length of the paired list produced by the zip function, which always matches the length of the shortest original list. In this example, the scores list is shorter, so the paired list will have that same shorter length. This behavior shows that zip automatically stops at the end of the shortest input list. As a result, it prevents out-of-bounds errors by never trying to access elements that do not exist. To find students who were not matched with scores, we take a slice of the students list starting at the position equal to the length of the paired list. This slice contains any remaining students who did not get a corresponding score. This step makes it clear that the zip operation stops pairing as soon as it reaches the end of the shorter list, leaving extra students unpaired at the end of the longer list. This script shows how the zip function works when combining lists of different lengths. It uses a list of student names and a shorter list of scores, and when they are zipped together, only pairs up to the length of the shorter scores list are created. Any extra elements in the longer list, such as the last student Dana, are left out of the paired result. The script prints the lengths of the original lists and the paired list to emphasize that the paired list matches the length of the shorter list, and then identifies the leftover unpaired student. Transforming with map filter. Mapping with built-ins. In Python, the map function lets you apply a chosen function to every element in one or more sequences, producing a new sequence of transformed values without changing the original data. It is especially useful with built-in functions for tasks like converting data types or adjusting text. For example, you can turn survey responses from text into integers or make product names lowercase. Using map makes these kinds of transformations clearer and less error-prone than writing explicit loops. Using built-in functions with map lets you transform a whole collection in one step instead of handling each item with a loop. For example, you can round a list of prices to 2 decimal places or clean up text by trimming spaces and standardizing letter case across all entries at once. This makes your code shorter and easier to read because it emphasizes what transformation you want to apply rather than the details of how you iterate through the data. Using the mat function with multiple input sequences lets you apply built-in operations to several lists at once, such as matching each measurement with its corresponding scaling factor without manual indexing. This same idea appears in machine learning, where you can convert different types of inputs into a uniform format by processing parallel sequences together. Overall, MAP helps you express complex data transformations as simple, high-level operations on entire datasets, which makes your code clearer and easier to maintain. Python code, mapping with built-ins. Use mapping with built-in functions to quickly transform everyday data. For example, you can take survey responses stored as text and convert them to integers by applying the integer conversion function to each response. In a similar way, you can standardize product names by mapping over them with the functions that make text lowercase and remove extra spaces. This approach helps clean and prepare data efficiently using simple, reusable operations. We begin with a list of survey responses stored as text, where each item is a number written as a string, and some entries have extra spaces at the beginning or end. We also have a list of product names that are written inconsistently, with different capitalization and unnecessary spaces around the names. These 2 lists provide the raw, messy data that the following code will clean up and standardize. We start by cleaning the survey data by turning each response, which is stored as text, into an integer using a conversion function applied across the list. This gives us a new list of numeric values that is easier to analyze. We then standardize product names by converting each one to lowercase, again by applying a conversion method across the list. The result is a cleaned list of product names with consistent formatting. We begin by cleaning the product names using a function that removes any extra spaces at the beginning or end of each name, giving us a list of neatly trimmed names. After that, we create a list of product prices in dollars. These prices are stored as decimal numbers, with each value representing the cost of a corresponding product. We first round each price in the list to the nearest whole dollar, using a mapping step that applies the rounding operation to every value. After this transformation, we print the cleaned survey numbers, which are now stored as integers instead of their original string form. This final output gives a clear view of the processed and standardized survey data. We first standardize the product names by converting them to lowercase and trimming extra spaces so they are consistent. Then we display the prices after rounding them to the nearest whole dollar. This rounding makes the prices easier to read and more convenient for later calculations or display. We create a list of product name lengths by using a mapping operation with the length function on each cleaned product name. This produces a new list of integers where each number shows how many characters are in a given name. We then print these lengths to quickly see the character count for each standardized product name and get an overview of their relative sizes. This script shows how to use Python's map function with built-in tools to quickly clean and transform data. It converts survey responses stored as numeric strings into integers, then standardizes product names by making them lowercase and trimming extra spaces. It also rounds product prices to whole dollars and calculates the length of each cleaned product name. The results are lists of cleaned numbers, standardized names, rounded prices, and name lengths, demonstrating efficient data transformation with built-in functions. Filtering with predicates. Filtering is the process of selecting only those elements in a sequence that satisfy a specific yes or no condition, called a predicate. Unlike transforming data, which changes each element, filtering leaves elements unchanged and simply removes those that do not meet the criteria. It is similar to screening job applications to keep only qualified candidates, or checking sensor readings to keep only safe values. The key idea is that the predicate defines what counts as relevant, and the filter applies this rule consistently to every element in the sequence. Predicates in filtering are rules that decide which data to keep based on certain conditions. They can be simple, like checking if a number is positive, or more complex, like requiring a timestamp to fall within a specific date range. Predicates can also combine several attributes, such as selecting customers who bought something recently and spent more than a set amount. In practice, they are used to remove incomplete entries in data cleaning or to discard implausible measurements in scientific work. Each predicate encodes domain-specific knowledge and applies the same consistent test across any relevant dataset. When you apply filtering, you need to balance how strict your condition is with its impact on the data. If it is too strict, you may remove important borderline cases, and if it is too loose, you may keep too much noise, such as fraudulent or low-quality records. Think about how filtering fits into the overall workflow, for example, by cleaning survey responses before converting them into scores. In real-time systems, filtering can serve as an early gatekeeper that reduces data volume by focusing on high-priority alerts. Well-designed filtering conditions improve both the efficiency and clarity of your data analysis. Python code, filtering with predicates. This lesson shows how to filter a collection of values using simple yes or no functions together with the built-in filter tool. The predicate function decides which values are acceptable and which should be discarded, so only items that meet the condition are kept. By printing both the original data and the filtered results, you can clearly see how the predicate removes unwanted values while preserving the ones you care about. We define a function called the comfortable Fahrenheit checker that takes a temperature in Fahrenheit and decides if it falls within a typical household comfort range. Inside this function, a condition tests whether the temperature is at least 68 degrees and at most 75 degrees. If the temperature is within this range, the function returns true. Otherwise, it returns false. This makes the function a predicate that can be used to evaluate any given temperature for comfort. We begin with a list of room temperatures measured in degrees Fahrenheit, where each value is a reading from a different room. Some of these temperatures are below the comfortable range, some are above it, and some fall within the desired comfort zone. This collection of mixed readings will later be used to practice filtering and identify which temperatures count as comfortable. We use the filter function to apply our test for comfortable temperatures to the list of room readings. This process removes any values that do not satisfy the comfort condition, so we are left only with temperatures in the desired range. Because the filter function produces an iterator, we then convert it into a list, so the filtered results are easier to view and work with. We first print all the room temperature readings in Fahrenheit to get a complete view of the data before any filtering. This establishes a baseline for comparison. Then we print only the temperatures that meet the comfort criteria defined by our predicate function. Comparing these two outputs makes it clear which temperatures were considered comfortable and kept, demonstrating how the filtering process works. We display the list of comfortable temperatures in Fahrenheit, showing only the values that satisfy the condition defined by our predicate function. This filters out all other temperatures and highlights just the ones that matter for our analysis. As a result, it becomes easier to interpret the output and clearly see which temperatures fall within the comfortable range. This script shows how to filter a list of room temperatures using a predicate function to find comfortable values. The predicate checks whether each temperature is between 68 and 75 degrees Fahrenheit. The program first prints all the original temperature readings, then uses the filter operation with the predicate to build a new list of only the comfortable temperatures. It finally prints this filtered list, illustrating how filtering helps focus on relevant data by removing values that do not meet the criteria. Lambda functions in practice. Lambda functions are small, one-time functions that you define right where you need them, which is especially useful when mapping or filtering data. They keep the logic close to the data and remove the need for separate named functions. This makes them ideal for simple operations like converting temperatures, measuring word lengths, or rounding numbers. When combined with mapping, a lambda function clearly describes how each item in a list should change, helping make the code more concise and readable for uniform operations. Lambda functions are useful for filtering because they let you define the condition for keeping an item right where you use it. They act as simple yes or no tests, such as keeping only large transactions, students above a grade cutoff, or sensor readings in a safe range. Since the condition is written in line, the selection rule is easy to see without jumping around in the code. This is especially helpful when chaining multiple filters, like first selecting completed tasks and then narrowing them to those finished in the last week. Lambda functions are especially powerful when combined with mapping and filtering in data processing pipelines. They can be used to filter out unwanted items, such as incomplete survey responses or outlier measurements, and then to clean, standardize, or calibrate the remaining data. In business settings, they help focus on relevant records, like active customer accounts, and compute metrics such as engagement scores. Overall, Lambda functions support complex workflows by breaking them into a series of clear, concise processing steps. Python code, Lambda functions in practice. This section focuses on using Lambda functions together with common data processing tools. You will see how to apply Lambda functions with a mapping operation to perform simple transformations on each item in a collection. You will also learn how to use Lambda functions with a filtering operation to select only the items that meet a condition. Finally, you will combine mapping and filtering into a tiny data pipeline that first filters data and then transforms the remaining values. We begin with a list of temperature readings measured in degrees Fahrenheit over several days. This list serves as our sample data. We will use it to show how a Lambda function can transform each value in the list. In this case, the transformation will convert the Fahrenheit readings into their equivalent Celsius temperatures. We convert a list of temperatures from Fahrenheit to Celsius by using a mapping operation that applies the same calculation to each value. A small anonymous function performs the conversion by subtracting 32 from each Fahrenheit temperature, multiplying the result by 5, and then dividing by 9. This formula produces the corresponding Celsius temperature. Because the mapping step returns an iterator, we then turn it into a list to obtain the final collection of Celsius readings. We use a filter operation on the list of Celsius readings to keep only temperatures in a comfortable room range. A small checking function is applied to each reading to see if it falls between 18 and 24 degrees, including both limits. Any reading that meets this condition is kept, and all others are discarded. The result is a new list containing only the comfortable Celsius temperatures. We create a list of purchase amounts that hold several dollar values, each representing how much a different customer spent. This list serves as our basic data for analyzing transactions. Later, we will use it to filter and process purchases by their size, so we can concentrate on the more significant transactions. We focus on significant purchase amounts by filtering the list of transactions. A filtering function checks each amount and keeps only those that are at least 50. The resulting list, called large purchases, contains only these higher value transactions. This helps us concentrate on purchases above a chosen threshold that are more relevant for further analysis or reporting. We start with a list of large purchase amounts and use the map function to apply the same transformation to each one. This transformation is defined by a small anonymous function that takes a purchase amount and rounds it to 2 decimal places using the round function. The result is a new list where every large purchase has been consistently rounded, making the values cleaner, easier to read, and more convenient to work with. We begin by printing the original temperature readings in Fahrenheit to establish a baseline. Seeing these initial values helps us understand the raw data before any processing. This makes it easier to compare them with the converted Celsius values later and clearly see the effect of the transformation performed by the script. We take each temperature in the list of Celsius values and round it to 1 decimal place to make the readings easier to read. This rounding is done efficiently using a list comprehension that processes every value in the list. Finally, we display the resulting rounded values together as a clear list labeled as Celsius readings. We display only the comfortable Celsius temperatures by first filtering the readings with a lambda function that keeps values between 18 and 24 degrees. Each selected temperature is then rounded to 1 decimal place for clarity. This produces a concise list of readings that fall within the desired comfort range. We start by displaying the original list of purchase amounts to establish a baseline for comparison. Seeing these values first makes it easier to understand how they change when we later focus only on large purchases. By printing the original data, we can clearly observe the transformation and filtering that occur in the next steps. We finish by printing the list of large purchases after they have been filtered and rounded. This final output highlights only the significant transactions. Each value is shown with 2 decimal places to keep the amounts precise and easy to read. This script shows how to use Lambda functions together with map and filter to quickly process lists of data in Python. It first converts a list of Fahrenheit temperatures to Celsius, then filters the results to keep only values in a comfortable room temperature range. It also works with a list of purchase amounts, removing transactions under $50 and rounding the remaining values to 2 decimal places. When run, the script prints the original and processed temperature values, as well as the original and filtered purchase amounts, illustrating how Lambda functions can efficiently transform and select data. From iterators to collections, lists and tuples. Lazy iterators generate elements one at a time, which is efficient, but sometimes you need the entire sequence at once. In those cases, you can convert the iterator into a list or a tuple. A list gives you an ordered collection that you can change, such as updating student grades. A tuple gives you an ordered collection that cannot be changed, which is safer to share or store when you want the data to stay fixed, such as for logging results. When choosing between lists and tuples, think about how the data will be used over time. Use a list when you need to add, remove, or reorder items, such as when sorting or repeatedly processing data like sensor readings. Use a tuple when the data represents a fixed record that should not change, such as simulation settings or user profile information. In this way, tuples signal that the data is intended to be read only and help prevent accidental modifications. When deciding whether to convert a lazy iterator into a list or a tuple, focus on memory use and how you plan to work with the data. Lazy iterators are efficient for large data streams because they do not load everything into memory at once. Converting them forces all elements into memory, which is usually fine for small datasets but can be expensive for large ones. It is best to delay this conversion until you truly need it. Using a list if you plan to modify the data and a tuple if you want it to stay unchanged. For instance, you might process data with lazy iterators to save resources, then convert to a list for user interaction or to a tuple for stable storage. Python code, lists and tuples. Show how to turn lazy iterators into concrete collections like lists and tuples so their values can be reused later. Emphasize that a list created this way remains editable, allowing you to change or extend its contents. In contrast, a tuple created from the same iterator stays fixed and safely unchanged. Use an example that zips together names and scores, then convert the result first to a list for modification, and then to a tuple to preserve a final unchangeable snapshot. We begin by creating a list of student names such as Alice, Bob, Kara, and Dan, which gives us a simple collection of identifiers. Then we create a second list of scores, where each number represents a test result for a student in the same order as the names. By aligning these two lists, we can easily match each student with their corresponding score. This structure makes it straightforward to pair names and scores and to perform any further analysis we might need. We use the zip function to create a lazy iterator that pairs each student name with its corresponding score. But it does not actually produce the pairs until we convert it into a concrete structure like a list or a tuple. We then print the type of this object to confirm that it is a zip iterator. This helps us understand that zip returns an iterator first, which we can later transform into a more tangible collection when needed. We first convert the lazy iterator that pairs student names with their scores into a list so that we have an editable collection of tuples. Turning it into a list makes the data easier to work with and modify. We then print this list to check its contents and confirm that the name and score pairs are correctly formed and ready for any further changes. We change the second element in the list so that Bob's score becomes 94, showing that lists are mutable and their contents can be updated. After this modification, we print the list to confirm that it now includes Bob's new score. This illustrates how changing an item in a list is immediately reflected when the list is displayed. We take the current list of student name and score pairs and convert it into a tuple to make the data immutable. This conversion creates a fixed snapshot of the list at that moment in time. Any later changes to the original list will not affect this tuple. We then print the tuple to display its contents and highlight that it is now read-only. We first display the current state of the list to show that it can still be changed even after we create a tuple from it, demonstrating that lists in Python are mutable. We then display the tuple, which does not change despite any edits made to the original list. This contrast highlights that tuples are immutable, meaning that once they are created, their contents cannot be altered. This example shows how a lazy iterator can be converted into a list and then into a tuple to highlight their different behaviors. The iterator first pairs student names with their scores, but once it is turned into a list, the data becomes editable, such as changing a student's score. This demonstrates that lists are mutable. When that list is then converted into a tuple, it creates an immutable snapshot of the data at that moment. The tuple does not change even if the original list is modified later, which is useful when you need a fixed record of the data while still being able to update a separate, mutable version. Building dicts with zip. A practical way to turn the temporary results of a combined iterator into something useful is to build a dictionary from it. By pairing two sequences, such as identifiers and values, you create direct mappings, so you can look up each value by a meaningful label instead of by position in a list. This converts a short-lived sequence of tuples into a stable, indexable collection that you can query and update throughout your program. As a result, you no longer have to worry about the iterator being exhausted or changing while you work with the data. When building a dictionary from paired data, you must handle different lengths and duplicate keys carefully because they affect the final result. If the two input sequences are not the same length, pairing stops as soon as one ends, and any extra items in the logger sequence are silently ignored, which can cause data loss if you are not expecting it. You may need to check lengths beforehand to be sure nothing important is dropped. Also, if the data contains duplicate keys, later values replace earlier ones, so only the most recent value for each key is kept, such as storing only an employee's latest department for a given ID. You can think of a dictionary as the final, stable form of paired data that you want to access quickly. You might start with a stream of raw data from a file or service, clean it, and pair related pieces, such as sensor IDs with their readings or configuration names with their values. Once you convert this paired data into a dictionary, you get a durable mapping that lets you look up information efficiently by key. This makes the dictionary a reusable structure that matches how your application or analysis needs to access the data. Python code, building dicts with zip. This section explains how to build dictionaries from pairs of values created by zipping together simple product data. It highlights that when the two zipped sequences have different lengths, any extra values or labels are silently ignored and do not appear in the resulting dictionary. It also shows that if there are duplicate keys in the zipped pairs, the later values overwrite earlier ones. Overall, the focus is on understanding how zipping and dictionary construction interact when lengths do not match or keys repeat. We begin with a list of product codes, which are simple labels for different products, and this list has 4 distinct entries. We also create a second list that holds stock counts, showing how many items are available for each product, but this list has only 3 values. As a result, one product code does not have a matching stock count. This mismatch is deliberate and is used to show how Python behaves when we combine these 2 lists into a dictionary using a zipping operation, where only pairs that exist in both lists are included. We use the zip function to pair each product code with a stock count, creating a lazy iterator that only produces these pairs when needed. We then convert this iterator into a dictionary, which maps each product code to its stock level for quick lookup. If there are more product codes than stock counts, any extra product codes are simply ignored because the zip function stops at the shortest input sequence. The code first prints a message explaining that the dictionary it is about to show was created by combining 2 lists of different lengths. It then prints the resulting dictionary, which pairs product codes with stock counts. Because the lists do not have the same number of elements, the extra product code at the end is ignored. This behavior is visible in the printed dictionary, where only pairs up to the length of the shorter list appear. We use a list of product codes, including one that appears twice, along with a matching list of prices to show how dictionaries handle duplicate keys. When we build a dictionary from these code and price pairs, the key that appears more than once cannot keep multiple values. Instead, the dictionary keeps only one entry for that key, and the later price in the list overwrites the earlier one. This demonstrates that in a dictionary, each key must be unique, and only the last associated value is stored when duplicates occur. We take 2 lists, one with product codes that may include duplicates and one with their prices, and combine them so each code is paired with a price. We then turn this combined sequence into a dictionary that maps each product code to a single price. When a code appears more than once, the dictionary keeps only the last price it encounters for that code. As a result, any earlier prices for the same code are overwritten. We introduce a new line of output to explain that the next dictionary will show how combining product codes and prices behaves when there are duplicate keys. When we display this dictionary, it reveals that if the same key appears more than once, only the last value paired with that key is kept. Earlier values for that key are overwritten. This demonstrates the general rule that Python dictionaries handle duplicate keys by preserving only the most recent associated value in the final result. This script shows how to build dictionaries in Python using zipped sequences. First, it pairs product codes with stock counts. And because there are more codes than counts, the extra code is ignored and only the first 3 codes get values. Then, it pairs product codes with prices, including a repeated code, and the dictionary keeps only the last price given for that repeated code. Together, these examples demonstrate that zip stops at the shortest input, and that dictionaries overwrite earlier values when the same key appears more than once. Iterator reuse limits. Lazy iterators that combine, transform, or filter data are usually single-use. You can think of them as a one-way conveyor belt. Once an item is taken, it is gone. When you loop over an iterator or convert it to a list, tuple, or dictionary, you consume all its elements. If you try to loop over it again afterward, it will be empty because the iterator is exhausted. This behavior differs from reusable collections like lists or strings, which you can traverse multiple times without losing data. When you turn an iterator, such as one producing sensor readings or database rows, into a list for sorting or slicing, you are taking a one-time snapshot of its data. After this, the iterator is used up, so trying to build another collection from that same iterator will give you nothing. To work with the data again, you must either recreate the original iterator or store its contents in a reusable collection from the start and perform all further processing on that stored data instead of the original iterator. Understanding how many times you can reuse an iterator helps you design efficient data processing workflows. For large or continuous data streams, such as financial transactions, you usually treat the iterator as a single pass to avoid the memory cost of converting it to a collection. For fixed data sets, like survey results, you might convert the iterator into a collection early, so you can traverse the data multiple times for analysis. The main decision is whether to keep the iterator as a one-time stream or store its contents for repeated access. Python code, iterator reuse limits. This lesson shows how a single-use iterator, such as one produced by a mapping operation, can be converted to a list only once. After the first conversion, the iterator is exhausted, so a second attempt to turn it into a list produces an empty result. In contrast, a list itself is reusable and can be iterated over multiple times without losing its contents. The goal is to clearly compare this one-time behavior of iterators with the reusable nature of lists. We begin with a list of lengths measured in feet, then use a mapping operation with a small anonymous function to process each value. This function multiplies each length by 12 to convert it from feet to inches. The mapping step creates a lazy iterator, meaning the conversions are not actually carried out until we use them. Finally, we turn this iterator into a list, which performs all the conversions and produces a list of the lengths in inches. We first create and print a list of lengths in inches by mapping a conversion factor of 12 over an original list of lengths in feet. This mapping uses an iterator, which is fully consumed during the first conversion. When we then try to build a second list from that same iterator, it produces an empty list because the iterator has already been exhausted. Printing this empty list demonstrates that iterators can only be used once in this way. We use a list comprehension to convert each value in the list of numbers measured in feet into inches by multiplying by 12, creating a new list of inch values. This new list is fully populated with the converted numbers and can be reused as needed. When we print the list multiple times, it always shows the same inch values. This demonstrates that unlike iterators, which can be exhausted, lists retain their data and can be accessed repeatedly. This material explains the difference between iterators and lists in Python using a length conversion example. A map-based iterator converts feet to inches lazily, and when it is turned into a list the first time, it processes all values. If you try to convert that same iterator again, it produces an empty list because it has already been exhausted. In contrast, a list created with a list comprehension stores all the converted values and can be reused as many times as needed. The main point is that iterators are single-use, while lists retain their data and can be accessed repeatedly. In this lecture, you learn to use zip to combine multiple iterables into tuples, handling length mismatches appropriately, apply map and filter to transform and select elements from iterables using functions or lambdas, and convert lazy iterators from zip, map, and filter into concrete collections using other built-ins when needed. In the next module, Module 5, we will go over functional style tools.
Thank you for your attention. See you all in the next lecture.